Thanks very much. I assume the people on Zoom can hear me all right. Everybody's good? All right, great.
Great.
Thanks again for having me. And it's a small enough group. If people have questions, please shout them out. Or if you've seen something in the news that you think is related to what I'm talking about, or you want a little more detail, or you're confused or something, just shout it out. I can deal with questions in real time. I'll start by saying I'm a theoretical astrophysicist. It means that I do a lot more computer work and calculations associated with astrophysics than I do actual observing, but I do have a nice Orion 8-inch that I use in the backyard. And I haven't done any imaging actually, except professional imaging, and there I collaborate with real, observers who do that for a living, but I am interested in that, and it's a lot of fun. So, okay. So today I'm going to talk about a bunch of different things related to supernova explosions and how galaxies evolve and various things. And I'll start with a question. Anybody know what this one is? Anybody recognize this guy? Say it again? Cassay. That's great. I just gave a public talk a couple days ago, and it was a very different audience, the kind of audience where no one would know that that's Cassay. Anyway, that's Cassay, Cassiopeia. What? Go ahead.
We're called Cass. So.
Yeah, that's right. That's right. Cassay. Good. Here we go. So some things you probably already know is that there are about 100 billion stars in the Milky Way. Those stars range in mass. When you go outside and you just look around, you see low mass stars and high mass stars. You see giants. You see main sequence stars. And those 100 billion stars range in mass from 0.1 times the mass of the sun to about 100 or maybe 200 times the mass of the sun. 0.1 times the mass of the sun is easy in the sense we understand that blobs of gas more massive than 0.1 times the mass of the sun actually undergo fusion in their cores. And blobs of gas below 0.1 solar masses, 0.1 times the mass of the sun, simply do not have the core temperature to undergo proton fusion. For at 100 solar masses, what sets the upper limit of stars, we don't even really know. So that's actually a debated fact. Why aren't there 300, 400, 500, 600 solar mass stars? That's still an open question as far as we would say. This picture in particular is of Carina. This is Eta Carina right there. One of the most massive, if not the most massive star in the entire galaxy. Actually a binary system, and may even have undergone a merger of two stars when it went through an outburst over 100 years ago. So there are clouds of gas. Those clouds of gas collapse to form stars. Those stars are 0.1 to 100 solar masses. And I said you see stars of all masses, but this is one of your buddies. One everybody knows, even labeled here, Orion. Orion is great. I love showing Orion because first of all, it's almost all massive stars. Everybody know this guy? Beetle Juice, exactly. So there's Beetle Juice, there's Bellatrix, there's Safe, there's Rigel, there's Mintaka, Alnilam, and Alnitak, I think. Couple interesting tidbits. One, almost everybody here is a massive star. Two, Betelgeuse is a red supergiant. It's red, obviously appears red on the sky, beautiful. And because of that, we know that it's near the end of its life. Near the end of its life, probably within 1 million years, but it would be more exciting if it exploded, 600 or so years ago, so that on the way home one day next year in winter, Betelgeuse will light up. That would be very exciting. That would be very exciting. I'd be very excited. One other cool thing about this that you might not know is that there are a bunch of multiple systems here. So Mintaka is a quintuple system, actually. Multiple massive stars and then a couple low mass stars around it. And Alnitak is a triple system too. Betelgeuse, lone star. Okay, so why am I talking about this? I'm talking about massive stars. I mentioned 0.1 solar masses to 100 or 200 solar masses. All stars, while they're on the main sequence and the main part of their life, burn hydrogen into helium via various nuclear processes. And for the sun, once you burn hydrogen into helium and then helium successfully burns into carbon and oxygen, that's the end of the story. And the reason the sun doesn't go any higher than burning hydrogen into helium and then helium into carbon and oxygen is because it's not massive enough. If it was more massive, it would be hotter in its core after those stages, and it would be able to burn further up the periodic table. More massive stars, sort of 4 to 8 solar masses or so, get one more stage of burning from carbon and oxygen to oxygen, neon, and magnesium. But they also end their lives as white dwarfs, and that's basically the end of the story. For 10 solar mass stars and above, you burn all the way to iron. So if you imagine the periodic table, everybody imagine the periodic table, hydrogen, helium, blah, 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 up to 26, which is iron. So iron is kind of in the middle top of the periodic table. And you burn all the way to iron, and you can't burn beyond iron. You can't burn beyond iron because if you try to fuse iron nuclei together, the reaction is actually endothermic, and it absorbs energy instead of releasing energy. So stars are born every year in our galaxy. Most people, even people who take beautiful pictures of galaxies, sort of think about them as static things that exist in the ether, sort of unchanging. Lots of people think that because they see just pictures in the magazines, you know, they don't think of them as time-changing systems. But our galaxy, what does it do? It takes gas and makes new stars. That's what it does. It's a factory for star formation. Every year, approximately every year, one new star about the mass of our sun is made. About every 100 years, a massive star is made. And because every 100 years a massive star is made, in equilibrium, about one dies every century, and we're waiting for that next supernova. Maybe it'll be Beetle Juice. And before they die, they get big and red and luminous, just like Beetle Juice. And there's a last day to these stars. You know, a 10 solar mass star lives for a very short amount of time compared to the sun, about 10 million years. Sun will live for about 10 billion years. Massive stars live for around 10 million years, but each stage is shorter and shorter. The hydrogen burning phase into helium is shorter than helium into carbon and oxygen is shorter than the next stage. Each stage is shorter. The stage of carbon burning only lasts for about 1,000 years. And then there's really one last day, one day, where there's silicon burning into iron. So at the beginning of that day, there's basically no iron nuclei in the core. And the star is going crazy, fusing silicon atoms into iron and iron peak elements around there. And it's incredibly inefficient, and it has to burn like crazy. And in that one day, it burns between 1 and 2 solar masses of silicon into iron. And then it gets to the end of that, and that's it. It can't do anything else. Its entire life, it's spent trying to hold itself up against gravity, just like you and me. Right now, you're holding yourself up against gravity. How are you doing it? Well, I'm doing it with bean burrito, actually, or maybe frosted mini wheats and some yogurt this morning. So we eat food, we take that, we break and make chemical bonds, and when we do, we get a tiny amount of energy, about 1 electron volt per chemical bond or so. Sun is holding itself up all the time against gravity. This star is holding itself all the way up against gravity, and it's each stage it's fighting against gravity, and here it encounters wholesale collapse. There's no fusion source that can stave off collapse. And it falls in on itself at almost the speed of light, about 1/10 the speed of light, when it finally hits that instability. Now, this is not at all to scale. The hydrogen envelope of Beetle Juice is huge, multiple times the distance from the sun to the Earth, 1 astronomical unit, whereas the iron core is about the size of Earth. It's incredibly tiny. And some of the videos I'm going to show you, the movies I'm going to show you later, are of the inner part, only a few hundred kilometers across on the inside is what we're gonna focus on. So this comes along, and then the star fails, and we're hoping that will happen. And we know, amazingly, we know that somehow this collapse leads to explosion. Now, this is a picture from the Southern Hemisphere. How many people have been to the Southern Hemisphere? Anybody? All right. So if you've ever been to the Southern Hemisphere, it's a gorgeous sky there. I've only been once. I spent a couple weeks in Santiago, and I got to go up into the mountains, not to a real observatory, but to an amateur observatory. I put amateur in quotation marks because the guy had a meter. No, it was a half meter. It's a half-meter scope, and I got to look through the eyepiece at the clouds. Anyway, it's a very spectacular experience, super fun for me. So here is, this is from the VLT, the European telescope in Chile. There's the galaxy, dust lanes, small and large Magellanic Clouds. And we know that collapse leads to explosion because we've seen it. We've seen that explosion. So 1987A is this very famous case, supernova 1987A, which occurred in that large Magellanic Cloud. There was a star that had been recorded at this position, an evolved star, not exactly like Betelgeuse, but a little bit like Betelgeuse. It's a supergiant, not so red. It was actually pretty yellow. But anyway, it got to the end of its life and it exploded. So that's the most nearby supernova in modern times, 1987. I was 12, 150,000 years before that, it exploded, and the light took that time to get to us. Maybe some of you looked at it or saw it. I don't know. There are lots of other cases where we've seen explosions. I'll give you another famous example, one that you've looked at. So here you can see Orion. There's Taurus, although I can barely see it. And right about up there, somewhere is your buddy M1, the Crab Nebula. And in July of 1054, 4th of July, 1054, only 1,000 years ago, the Chinese had watchers of the sky who would sit on rooftops and in dark places and record anything that changed at that time. And often they recorded them as guest stars, sometimes noting that they had some outgassing or something interesting. Those were probably comets. And in other cases, the guest stars were supernovae. And this one, they recorded, visible for 23 days. They recorded it, a bright light in the sky. And of course, they didn't see the star before it exploded because it's too far away. But now when we turn our telescopes to the position of that the Chinese recorded at kind of the tip of where Taurus and Orion come together, we see the Crab Nebula. So this is a beautiful picture of the Crab Nebula. It's a composite of a bunch of different things, and you can see this with your own telescope, not quite in such detail, but you'll see a beautiful oblong smudge with a decent telescope, and if you get lucky, you might see a little structure. And in the center, of course, you don't have an X-ray telescope, but if you did, if you were piloting an X-ray telescope, the Chandra X-ray telescope, and you pointed it at the center of the Crab Nebula, what you would see is the Crab Pulsar, a neutron star left behind from that supernova that happened just about 1,000 years ago. And it's rotating around with the spin period of some ridiculous time, like 30 milliseconds. It rotates, it has a huge, super strong magnetic field, and it sends out these ribbons of energy and radiation, kind of powering the central nebula of the Crab. So we know that supernovae happen. We know that this collapse can turn into an explosion. Betelgeuse, if it happens, would be brighter than the full moon, or about the brightness of the full moon for 100 days. 100 days. Just think about that. That would be so sweet. I can't imagine. Of course, it'd be cloudy in Columbus, but not for 100 days. Not for 100 days. We get at least a good look at it. Yeah, it would cast shadows. It would cast shadows for 100 days. Pretty cool. Anyway, why do we care about supernova explosions? Well, they're awesome, they're beautiful, but we have a real reason. Carl Sagan's famous quote. Carl Sagan has many famous quotes. One of them is, "We are stardust." Another one is, "If you wish to make an apple pie from scratch, you must first invent the universe." Why? It's really, you could talk about any of these layers, but my favorite one to talk about is oxygen. Oxygen. So I often bring this up. Has anybody ever heard of the law of threes? Law of threes. You can survive 3 weeks without food, 3 days without water, 3 minutes without air. So let's look at that. So I said I was powered by, yogurt and mini wheats. One of my favorite things in yogurt and mini wheats is C6H12O6. That's a simple sugar. C6H12O6. All the H is from the Big Bang. All the C Partially, there's a layer of C here, but a lot of the carbon is from lower mass stars. But all the oxygen atoms, every single oxygen atom is from a supernova explosion. All of them. So that's the food, okay? But we also drink water. Many of you are familiar with the chemical composition of water, H2O. H is from the Big Bang. Oxygen is from this, okay? If you haven't had any water now, you will soon, because you need it or you'll be dead. Air, O2. O2 and N2. N2, you don't care so much about, your body doesn't do a lot with, but your body does a lot with O2, molecular oxygen. Again, every single one of those oxygen atoms required for you to breathe, drink, and eat is from supernova explosions, which I think is amazing. I never get tired of saying that. So now this stuff, this is Cas A again. This particular image is in a certain transition of silicon taken in X-rays. And so these are the silicon atoms literally from this inner region flying outwards at multiple millions of miles per hour in a supernova blast wave. This supernova probably occurred a couple hundred years ago, but it was not seen by many, and not well recorded. So how do these atoms end up in our water? You know, supernovae feel like rare events. We're humans. We live for maybe 100 years or so, and it feels rare once every century to have a supernova. But here's a galaxy, a pretty one, NGC 6946, one of my favorites. Beautiful, near face-on spiral galaxy. And a supernova is going off here every 100 years. But you have to remember, you can imagine like the solar system is 8 kiloparsecs or so from the center, about 25,000 light years from the center of the Milky Way. This is a little bit like a Milky Way-like galaxy. You can imagine us orbiting out around here. And how long does it take for one turning of a galaxy? Anybody know? Say it again, 200 million years? 400 million. Oh, it's more than that. It's about 200 million years. 200 million years to go around once. So, you know, if we're here, then, you know, the dinosaurs went extinct like 1/4 of a tick ago, 65 million years ago at the end of the Cretaceous. But here, if you imagine one rotation, 200 million years, and there's a supernova every 100 years, that's 2 million explosions. 2 million in one rotation. So you should imagine these massive stars, some of them you can see these actually massive star complexes here. You imagine them popping off 1 million or 2 million per turn. And those supernovae explode into the medium. And as they explode, this one is a young supernova remnant moving fast. But as it explodes into the surrounding interstellar medium, that blast wave slows down. And when it slows down, it creates a gaseous nebula that is enriched by these elements. And then those collapse to form new stars. Just like in the Carina Nebula I showed you at the beginning, with Eta Carina, the bright star off to the side, those are gas blobs that are collapsing from previously enriched gas. And as this cycle continues and the galaxy whirs around, you know, the sun's been around 20 times or something. Massive star only makes it a little ways before exploding and enriching the medium, exploding and enriching the medium, exploding and enriching the medium. And the sun and the solar system formed out of all this enriched material. And that's where those oxygen atoms came from. Okay, so supernovae. What do we think actually happens? I'm a theorist after all. This is what we think actually happens. So what do we need to do? So how do supernovae happen? There are a lot of steps here. I'm gonna show you a few words here, and then I'm gonna show you a couple movies. You first have to compute the massive star evolution. I sketched that for you, but basically you start with a huge ball of hydrogen and you let it evolve. Core fuses hydrogen to helium and so on, successive stages. You need your nuclear physics. You need your balance between pressure and gravity everywhere to keep that star in what we call hydrostatic equilibrium. Then you write down equations that describe the matter at the core of this star, that describe the matter at ultra high temperatures and densities. You describe how fluids flow, how gases and fluids interact. And then you write down interactions and particle physics associated with exotic particles like neutrinos. Neutrinos are going to figure in here very strongly. Then you solve these equations, You see what happens. You cross your fingers, you press enter on your supercomputer, and then you walk away. Now, okay, a few words about neutrinos. One is that neutrinos are a byproduct of nuclear fusion. Right now, the sun, which direction am I pointing? Is that south? Yeah. That's south. West. Sun. So the sun right now is undergoing fusion, protons into helium. There's something in the range of some ridiculous number, like 600 million tons of hydrogen is converted to helium per second in the sun. And every time you convert hydrogen into helium, you produce the helium, you produce energy, and you produce neutrinos. And those neutrinos, these subatomic particles that are incredibly weakly interacting, come flying out of the sun unimpeded, right through the Earth right now, right through each of us, 60 million per square centimeter per second, all the time. Right through the Earth, because the Earth is completely transparent to these neutrinos. Amazingly, if you set up a water detector that's big enough and you wait long enough, you'll eventually see the blink of one of these neutrinos. And that won the Nobel Prize and is an amazing confirmation that we actually know what the heck is going on in the center of the sun. I teach these general education courses, and I have 250 undergraduate students, and periodically it comes up like, why should you believe in what I'm telling you? The students want to know. I mean, I say things like I know what I'm talking about, but why should you actually believe that there's fusion going on? What's amazing is that the number of neutrinos can be predicted. You predict the number of neutrinos, then you set up your water detector and you detect the number of neutrinos, and that's how you know that it's actually fusion going on there. Anyway, those neutrinos also come from lots of different nuclear reactions, and they figure very prominently in this. What you've probably heard is that supernovae produce neutron stars, and I actually mentioned that a second ago when I was talking about the Crab Nebula M1. Supernovae produce neutron stars, but maybe you've never seen the actual chemical reaction that gives rise to a neutron star. This is it. This is the chemical reaction. So imagine you have this iron core. The star's been sitting there for 10 million years, and in its last day, it burns silicon into iron. The iron is sitting there, it can't support itself anymore, gravity wins, and as the material is collapsing, what's iron made of? Well, 26 protons, 30 neutrons, and a bunch of electrons, 26 electrons for charged neutral iron. But these iron nuclei are getting compressed into higher and higher densities. And when that happens, the electrons that were hanging around the iron can combine with the proton from the iron nucleus. And when they do, they make a neutron. So this process right there is how you make a neutron star. And it's why it's called a neutron star, is because it's made almost entirely of neutrons, because you took all the protons you had and all the electrons that you had, you mushed them together, and you get neutrons. Now, in order to make this process work, that has to release also a neutrino. Same kind of neutrinos, or some of the same kind of neutrinos we get from the sun. And so what you predict is that when the core is collapsing, you basically take an entire 1 or 2 solar masses of iron and you convert it into neutrons and neutrinos. And that should produce a huge burst of neutrinos that we could potentially observe. And the best guess right now, this again in words, I'll show you in pictures in a second, is that when that core is converted to neutrinos, or to neutrons, and those neutrinos stream out, that the neutrinos can actually heat the star that's above it, and that blows the thing up. That's how you turn that collapse into an explosion. So here's a movie, which I'm going to spend some time describing. This movie is from an ancient calculation from the last millennium, 1995, but it has some pedagogical purposes. And so what you're seeing here is a computer calculation on a supercomputer at that time, which is not now. And this is the center of the star. So we got a star like Beetle Juice. Here's the center of the star. This is just the inner 300 kilometers. Remember I said the iron core was about the size of Earth, and the hydrogen envelope is in, I don't know, on this scale, it's like in Dayton. This is just the inner core, okay? Now, what's going to happen is that I'm going to push the movie and time is going to go by. This says 0.1 seconds for the people in the back is 0.1 seconds, and it's going to get to about 0.35. So about 0.25, a quarter of a second is going to go by. And what you're going to see is this whole thing is going to collapse into the center. You're just seeing one quadrant of the star. The whole thing is going to collapse into the center. And what happens is this reaction is going to produce a burst of neutrinos, which you're not going to really see. But what you are going to see is a neutron star forming here. And then you're going to see some boiling and roiling. Basically, the boiling is caused by the fact that all these neutrinos are streaming out. Meanwhile, the iron core is collapsing, collapsing, collapsing. The iron core keeps collapsing because once the rug is pulled out from under the iron core, everything falls in. It would be like right now, if the Earth was shrunk to a foot across at the center, we would all just fall. That's what would happen. We'd fall. It'd take us 90 minutes or maybe 45 minutes to get to the center of the Earth. But that's what everything is doing, is everything is falling in. Okay. So here's what happens. There's collapse right there. That's collapse. This is the neutron star forming. There's neutrinos streaming out of here, and the iron core is collapsing. And what you see is that there starts to be convection. It's actually just like your hot pot when you boil water. When you boil water, it's hot on the bottom and cooler on the top, and so it convects. And then it suddenly explodes. I'll show the movie again. This is the explosion happening. So again, we have collapse, the neutron star forms. Neutrinos streaming out, matter falling in, matter falling in, matter falling in. Boiling and roiling, and here's this shock wave that's just sitting here. You can see it's kind of stable. And then after a little while, you'll watch this thing and it'll just move out. Move out, as if a critical amount of heating had been deposited, and all of a sudden it moves out. And stuff still wants to fall down. This is all happening in a few tenths of a second. And you can see stuff wanting to fall down, and it gets pushed back out. And you leave behind this neutron star here. That's the picture that we have. And just like the students in my class, when I describe fusion processes in the neutrinos, you would say, why should I believe that? Why should I believe that? And the answer is that in 1987A, supernova 1987A, was accompanied by the detection of a burst of 20 neutrinos. 20 neutrinos over 10 seconds. So that neutron star collapsed and sent out a wave of neutrinos. And then that neutron star sits there and radiates neutrinos for 10 seconds. And the total energy we measured in those neutrinos, the time scale, this 10 seconds, the spectrum of those neutrinos, were all precisely consistent with expectations from those types of models. Yeah, so let's talk about just how dense this is. So you float. You float. If you fill your lungs with air and jump in the water, you float. If you get all the air out of your lungs, you sink. You're neutrally buoyant in water. Your density is the density of water. You're basically 1 gram per cubic centimeter. So you take a cubic centimeter, there's a cubic centimeter of Todd, that part is a gram, 1 gram per cubic centimeter. This is, right there is 100 trillion grams per cubic centimeter. This is about 1 trillion grams per cubic centimeter. This is in the neighborhood of sort of 100 billion grams per cubic centimeter. So actually, the neutrinos take a while to get out of here. Because you'll sometimes read in popular science, neutrinos can pass through a light year of lead or something like that because they fly through the Earth all the time. It's true, but the Earth's density is basically just the density of an iron ball, 5-6 grams per cubic centimeter. You know, the densest rock you've ever picked up, if you've picked up dense rocks, the densest rock you've ever picked off the ground or anywhere is an iron nickel meteorite. If you've been lucky enough to see one, sucker's dense. You pick it up, you're like, wow, that is dense. But we're talking, 100 trillion times that or 50 trillion times that. So it's incredibly dense. And that's why, so the neutrinos are actually leaking out of here, and then they heat all this matter as they move forward. So this is one case, one of the few cases in nature where neutrinos take a long time to do what they're doing. So this takes seconds or even 1/10 of a second, and that is very long. On this scale. Temperatures here, I should say, temperatures here are about they're about 10 billion to 20 billion Kelvin, in that range. For reference, the center of the sun is about 15 million. So this is a little bit more than 1,000 times that temperature. Other questions? So this is why you should believe it, because we actually saw, this was predicted. The neutrino signal was predicted. The neutrino signal from converting this. And there were neutrino detectors at that time, one of them called Kamioka, and another one called the Irvine, Michigan Brookhaven telescope. And they saw these neutrinos, and those people won the Nobel Prize for that, detection of neutrinos. Now, I showed you an ancient simulation. Here's a more recent simulation. This is 2018. This is, again, a neutron star. There's time ticking by there, 1/10 of a second, 0.15, 0.17. And there's going to be some boiling and roiling here. And this is actually the explosion developing over about a 1/2 a second time scale. I'll show it one more time. So again, the neutron star forms very fast. The neutron star, the whole thing collapses. And you might wonder, two questions that might come to mind is, why does a neutron star not collapse itself? So that's the first question. Why does a neutron star not collapse itself? And the reason is that the neutron star here at the center is like a huge nucleus. You're used to nucleus, I described before, iron nucleus, 26 protons, 30 neutrons. So here is in the neighborhood of, I should know that number. It's in the neighborhood of about 10 to the 57 neutrons, but it's basically a nucleus. It's the same density as a nucleus. It's just 10 to the 57 nucleons instead of your normal iron nucleus. So this thing is supported actually by the strong nuclear force. The thing that holds nuclei together is what holds this thing up. What holds this thing up? And the other question you might have is materials raining down on here, falling down, and yet these blobs are moving outwards because they're being forced by the neutrino heating, all the neutrinos streaming out here and heating. Yeah, that's what I wanted to say about that. What's the spatial scale of this? Yeah, so the core, the best thing to think about it is that the iron core is about the size of the Earth. And then when it collapses, this thing is about 20 kilometers across. So if you were a good runner, I'm not a good runner, but if you were a good runner, you could run it in a day. 20 kilometers, I don't know. Not for me. 2 kilometers, maybe 2 kilometers, but 20 kilometers or so at first. And what happens is that a neutron star, after it's cooled off a bit, is more like about 10 kilometers. So you can think about it as, I don't know, 270. I don't know, roughly, like a sphere that's 20 kilometers across is like 270, the loop around Columbus. But we went from the Earth to that in a little less than 1/10 of a second. And then the rest of the star, the silicon layer and everything is falling in. And then this explosion develops. And this is, you're only seeing scales, that's only 10 kilometers. And so what you might wonder is, what does it look like when it totally destroys the star? And so here's larger scales. Now you can see many seconds going by. Many seconds going by, the neutron star is way down here and it sends this shock wave into the star. The poor star is sitting there, has no idea what horrible thing is going on inside it. The surface of the star is still way out there. You still haven't seen the surface of the star. It'll take thousands of seconds for the shock wave to get to the surface of the star. So the central neutron star sends out this explosion, the shock wave moves in, there's all these rarefactions that are happening, all these things that are shocking. There's the edge. This is finally the edge of the star, 20,000 seconds after the supernova happens, is finally when the edge of the star knows what horrible thing has befallen it. So this is a pretty old supernova simulation, but it's from 2006. There are others that I could have shown you, but I think this one's particularly pretty. It's really interesting that the core just keeps on pulsing. Yeah, no, the reason the core down here is doing some pulsing is actually it's a numerical thing. It's that they're trying to adjust that inner boundary as all this other stuff is happening. So that is unfortunately an artifact of the simulation. But yeah, this is the way you should imagine a star being disassembled. And then the question is, does this actually look like real life? And the answer is, let me see if I can get the right. The answer is that, those neutrinos matched almost exactly. The neutrinos were great. They matched almost exactly for 1987A. But the models that we build, too few stars explode and with too little energy. So when we actually try to compare those types of calculations to real supernova explosions, we see that they don't really have quite the amount of energy that they need, and more stars don't explode than should. We think that more stars should explode. So maybe there are missing pieces. Maybe there's more than just the neutrinos. How do we make sense of that? Here's another simulation that's not interesting at all. It just collapses to a black hole. And so what happens is that you form your neutron star, there's some boiling and roiling, and then it never reaches whatever criterion it needs to explode. And there's matter coming down and matter coming down and matter coming down, and it eventually reaches a critical, there's a critical mass. It's kind of a race to see whether or not the star is going to explode or collapse to a black hole. And the reason is, I mentioned that neutron stars are supported like a nucleus by the strong nuclear force, but there's a critical maximum mass. There's a critical maximum mass for that, it turns out. Go ahead. It's not the Chandrasekhar mass. So Chandrasekhar, I could describe the Chandrasekhar mass, it's related to it, so stay with me. What happens is that a neutron star supported like this, like a nucleus, has a maximum mass of about 2.5 times the sun's mass. Now let's remember, Beetle Juice, like 15 solar masses. Core is about 2 solar masses, 1.5 solar masses. Actually, the reason it collapses is because of the Chandrasekhar limit. So that collapses, forms this thing, forms this neutron star, but this whole star is falling in. The whole star is falling in means that the mass of this thing is growing. The mass of this is getting bigger. Every second that ticks by, 0.4 seconds, 0.5 seconds, 0.6 seconds, the mass of this thing gets bigger and bigger and bigger, closer and closer to that 2.5 limit. And when it does,
that's the TOV,
TOV equation, yes. Yeah, so if you solve the equation that Don's referring to is a Tolman-Oppenheimer-Volkoff equation that's used to solve for the structure of a neutron star. And when you put in everything we know about nuclear physics, you find this maximum mass. And it is distinct from the Chandrasekhar mass, if you've heard of that. And so what happens? What would failure look like? What do you think? Anybody? What happens if the star forms a black hole in its center? Any idea? What? Go ahead.
Start sucking it in.
So sort of blinks out. And here's the thing is, how would you find that? So how would you find that? So about 15 years ago, I started at Ohio State. I started at Ohio State in 2007. And I have 2 colleagues there who you've probably met before. If you haven't had them talk, you can have them talk. They're great. And my colleagues are Chris Kachanik and Chris Stanek. It's not a joke. Chris Kachanik, Chris Stanek, no relation. So Chris Kachanik and Chris Stanek and I and a couple of other people were standing around having this conversation. And there was a discussion of finding supernova explosions. Okay, it's easy, quote, to find supernova explosions. What you do is you look at galaxies again and again and again, and you look for a really bright thing. Supernovae are very bright. They outshine sometimes the whole galaxy. So you look at the galaxies and you look for a really bright thing. Piece of cake. If you find it, you record it, you study it. That's a supernova survey. We do those all the time. But what would you do to look for, as the gentleman says, a star that just goes away? Go ahead.
Maybe you would look for a star. So here's what I think would happen.
Yeah.
Core goes down to a supernova, but we're dealing with a red giant.
Right.
So you're left with a red giant with a black hole at the center, which is a couple times the mass of the sun.
Yep.
That star is going to become material for an accretion disk around that black hole.
Right.
And so the accretion disk is going to form in the core. And what's going to happen eventually is you'll get the jets out of the accretion.
And you'll get some power source.
And that'll blast the top and the bottom out. But I'm going to guess that that's going to happen a lot slower than a supernova. So it'll be a gradual process.
Yeah.
You'll get a gradual brightening.
So we didn't know because nobody ever seen it. Nobody ever seen that happen.
So one idea, as what was your name again?
Right.
Say it again.
Right.
I can't hear very well, but he was saying, Brad was just saying, is that the star, if the star is even slightly rotating and you form a black hole in the center, then maybe the material will come down and form an accretion disk and spiral in, and that will power jets or power some other energy. And there was another set of theories that once the star forms a black hole in its core, that actually, because you've radiated all this neutrinos, the hydrogen envelope, only the hydrogen puffy red giant part of the envelope would actually expand outwards. There were a bunch of different questions, but Chris Kachanik and Chris Stanek and I, we all were having this discussion, and Kachanik realized that what you could do is you could look at all the nearby galaxies, take 20 or 30 large spiral galaxies, 20, 30 large spiral galaxies, and you look with the large binocular telescope, which is two 8-meter mirrors, and you make a list of all the stars like Beetle Juice. You catalog every single one, 100,000 per galaxy, and you do that for 20, 30 galaxies, and then you've got 2-3 million of these things that look like Beetle Juice, 2-3 million stars that look like Beetle Juice, and then you just wait. On average, one of them does something, one of them will die every 1 million years, because that's how long that phase lasts. If you're looking at 2-3 million, that means that every year you should see 1 or 2, something should happen. And so the one option is that they explode as a supernova, and that's what he saw. On some of them, they exploded as a supernova, but one of them just went away. So this again is NGC 6946, which I actually showed you before. Very interesting galaxy for a lot of reasons. This is a Hubble Space Telescope image from 2007. And this image shows a Betelgeuse-like red supergiant in it, 100,000 times the luminosity of the sun, maybe 200,000 times the luminosity of the sun, sitting there doing its thing, looking like something bad is going to happen to it in the next 1 million years. Now, you all are in an astronomical society, and some of you specialize in imaging. So the star itself is tiny, tiny, tiny compared to this. This is blurry. The star is a minuscule speck in the middle of this, totally unresolved by this telescope. And here is an image from 2015 from Hubble. The pictures look different because Hubble was serviced between 2007 and 2015 and had a different camera. This is what's called WIFPIC 2, and this was WIFPIC 3. They're different cameras. They were installed at different times, taking pictures of the same location, but you can still, you can make out little asterisms and things. It's definitely, and so this is a star that just went away. And amazingly, Kachanik was taking data only about 3 times a year. It's very expensive to take this data. Only hitting the galaxy about 3 times a year, and they actually saw a little brightening of the star that was maybe associated with that puff of the hydrogen envelope coming off, and then that was it. So just silence since then. So many people, including me, in that discussion would have said, well, it's going to form an accretion disk, and there'll be jets, and there'll be some bright X-ray something, and we haven't seen anything. Chris hasn't seen anything. It's as if the star just vanished. There's no X-ray source. No.
Yes, go ahead.
Well, I was going to say that since normal, like Betelgeuse, is expected to do a big collapse.
Yep.
In other words, all the material starts moving inwards.
Yep.
And if the core goes to a black hole instead of, just a neutron star, then it's going to stop emitting neutrinos, because those don't escape black holes.
Yeah, they don't escape black holes, right?
So
it'll just collapse
that
in.
heating and roiling, that would be the big explosion.
Yeah, that's
you only get a little bit of that.
That's right.
And then it's gone.
That's correct. But at the same time, as Brad was just saying,
that outer part of the red supergiant would take almost a year to fall in. It would take a long time because it's such a big structure. And if it was rotating just a little bit, you might think that it would form something. And so they did see, so I don't actually have the light curve here, but the star is hanging around like this. You measure the star, you measure the star, you measure the star, you measure the star, then there's a little spike where it got a little brighter. And then there's this slow, steady, like half-year decline. And then there's just darkness. And so this is potentially the first observation by humans of actual black hole formation in real time. It's not clear. So JWST, as you know, presents a brand new capability for us. And JWST is right now beginning to take observations. And it has a mid and near infrared imaging and spectroscopy that Chris is going to look here to see whether or not we can see anything. But there is no X-ray source there. It just, poof, vanished. Yes. What's the gamma ray burst connection is there was no gamma ray burst from this. But I was going to talk a little bit more about GRBs, but I'll come back to it. Gamma ray bursts are flashes of gamma rays we see from the other side of the universe, all over the place. And those also, some of them come from massive stars. And those we do think are exactly when something is rapidly rotating and collapses and makes jets and so on. But here is a case where we don't see any of that. So I want to tell you a little more. So this is a theoretical calculation that I did with my PhD student, Andre Peja. And what we did is we analyzed the structure, the interior structure of stars of 10, 11, 12, 13, 14, 15, 16, these solar masses, right before they collapse. And using this neutrino mechanism, this neutrino heating thing, we're able to calculate whether or not the star should or should not explode on the basis of its initial mass. So you start with its initial mass, you run it forward in time, you take the structure when it collapses, and then you say, should the neutrino mechanism be able to explode this or not? If it is, you mark it green. If it doesn't, you mark it black. And if it might get close and be like, then you mark it orange. Okay. And so here's the thing is that we only went to 40 solar masses. There are details about that, but you know, Eta Carina is out here at 200 solar masses or 150 solar masses. And where's Beetle Juice? Best guess is Beetle Juice is there in the neighborhood of 15 to 16 solar masses, actually. So even though I so want Beetle Juice to explode and be as bright as the full moon for 100 days, Beetle Juice is right in the mass range that we think this other guy was, right in the 15, 16, 17 solar mass range, where sometimes we're right on the verge of explosion and sometimes we collapse. Now, why does this one form a black hole and this one doesn't? And this one doesn't. It's actually the shape of the iron core when it collapses is actually related to the Chandrasekhar mass and how the structure of the core is right when it explodes. So you can get this crazy non-monotonic is what we would say. It's not like a continuous function. It's not like everything above 25 solar masses collapses to a black hole, which is sometimes what you read. And that 15 solar mass stars always explode. On the contrary, there are certain stars right here that are very difficult to explode with these neutrino heating, and stars here that are easy. And 20 solar masses is easy, but 19 solar masses is hard. And 30 or 28 solar masses is hard, but 30 solar masses is easy. And why is that? It has to do with his structure. It has to do with his internal structure. So why is that important? You know, if no stars exploded, and every star formed a black hole, then nothing you know would exist. And if every star exploded, then we'd have no black holes, which we know exist. So there has to be a mapping between the initial mass of the star and maybe its binary companions, important detail, and the final outcome that gives us, you know, the universe that we have with this number of oxygen atoms and this many black holes. And that's what we've been trying to do. So that's one reason why we made this map, and we're trying to understand that neutrino mechanism in more detail. Yeah, Isaac?
Now, if we look at the edges, right, I mean, it's probably not binary, right? I mean, there is actually like a ragged edge in there.
There is a ragged edge, yeah, actually. And in fact, it's interesting. One of a postdoc who was at Ohio State did an incredibly high resolution version of this. Incredibly high resolution because there's a little bit of butterfly effect and chaos going on that many of you might know that some dynamical systems can't be predicted far into the future because there are nonlinear feedbacks and resonances that mean that you end up in a completely different state than you otherwise would. And this makes deciding whether or not a dynamical system is stable or the outcome is stable is super duper 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 sensitive, exponentially sensitive, in fact, to your initial conditions. So if you start with a star of 15.1251 solar masses, then you get a different outcome than 15.129 solar masses. And the difference is that the star is a totally connected thing that has all these dynamical processes going on in it, and none of it is reversible, and some of it can be chaotic. And so you end up with very ragged edges, and sometimes it's kind of indeterminate. There might just be, if you pick a star of this and you run it 100 times with slightly, just barely varying your code at the 15th digit place or something, then you might get different outcomes. And so you might need to think about it as like there's a certain probability of black hole formation and supernova that varies as a function of these parameters. Angular momentum does come into play. So this is a big issue. Stars rotate. Some stars rotate fast. Massive stars especially rotate fast. And so if you go say, well, here's stellar evolution. Here's everything we know about stellar evolution. We have one of the world's experts in our department, Mark Pinsino, is one of the world's experts of stellar evolution. And you say, okay, you evolve a star. Good for you. It goes through its stages. It does its nuclear burning, whatever. Now make it rotate. And they make it rotate. And there is no settled theory. There is no settled theory in astrophysics about the evolution of a star that's rotating. Wow. And that includes the sun, in fact. There are mysteries still about how the sun's angular momentum, how its rotation profile changes as a function of time that are unsolved. So we make theories of them. We have lots of theories of rotating stars. The literature is vast and covers, actually, since basically Mark's PhD thesis in the 80s, he's been a pioneer in rotating stars, not actually massive, but low mass stars like the sun. And we know tons now about it, but there is no first principles theory that I, the theorist, write down and say, these are the equations you use to evolve a rotating star. We still don't know that. We know that they rotate. We know they rotate. We're just limited. Yeah, for sure.
So you mentioned some of these really massive stars, of course, are multiple star systems. How does that happen? Can you have one of them, collapse before the other, and then how does that?
Yeah. So generically, binary systems are very common. In fact, almost all massive stars are in a binary or higher order system. In fact, Beetle Juice is the rarity as a single red supergiant. Most massive stars have a buddy, and a lot of them are close by, close enough that they're going to interact sometime in their evolution. If one is more massive than the other, which they almost always are, one is more massive than the other. Typical would be, a 20 solar mass star and a 15 solar mass star. The 20 solar mass star evolves first, and it's going to have one of these outcomes. It's going to collapse, and it's going to form a neutron star and explode, or a black hole and collapse. And then the buddy is going to do the same thing. And it could form two black holes. It could form two neutron stars. It could form a neutron star and a black hole. And then we see those. We see them in gravitational waves. We see those systems. I was going to show you. Hold on one second. I was just going to show you. I was going to show you this. I was trying to give you, I wanted to give you some reference points. This is the LIGO press release movie of their first detection. LIGO is a gravitational wave experiment. What it does is it measures perturbations in space-time that propagate across the universe as black holes and neutron stars merge together. And in about 2015, actually in 2014, but then released in 2015, they saw the merger of a nearly 40 solar mass black hole with a 26 solar mass black hole that must have been in a binary system. And this is just showing you the last few orbits. And this merger happened in a galaxy very, very, very far away. And this is a little gratuitous in the sense that they put the black hole merger in front of a Milky Way star field just so that you can see the perturbations of space as the actual merger is happening. And so you can see some of the lensing effects that would happen if you could see it in front of a star field. Of course, this happened in some galaxy far, far away on the other side of the universe. But nevertheless, it gives us a clue to the type of things I'm talking about, because here we have an actual 40 solar mass black hole with an actual 26 solar mass black hole that were in a binary system that somehow evolved to eventually produce those two black holes and then eventually merge here. And so that can happen. We can have those two black holes. We can also have two neutron stars. So here's a simulation from a guy I know, Stefan Roswag, of two neutron stars. Here, these are milliseconds ticking by. So that's 3 milliseconds, 4 milliseconds, 5 milliseconds. And so you have two neutron stars here. So imagine two successful supernovae producing two neutron stars that eventually merge together and form a black hole and also shed a bunch of material. And this has also now been seen by the LIGO Gravitational Wave Observatory. They've seen two neutron stars merge together to form a single black hole. But that also gives us information on which stars explode and which stars don't, and what the kind of outcomes you can get from these things are. I didn't actually talk very much about gamma ray bursts, but there are also gamma ray bursts. There are also very energetic supernovae. And I left you with the idea that we feel like something is missing. Something is missing from our models in explaining these very energetic supernovae, in explaining the observations of supernovae that we find. And if I had another hour to talk, I would tell you that what I think the answer is that it's not just neutrinos. I think it's also rotation and magnetic fields. So this gets back to angular momentum and other things. When I showed you the core collapse, all those two calculations I showed you, nothing was rotating. And yet neutron stars like the crab are rotating 30 times per second or something. And the crab has a relatively wimpy magnetic field. It's only about 1 trillion times the magnetic field of the Earth. But there are neutron stars with even larger magnetic field, 1,000 times bigger. And if you imagine the core collapsing to a rapidly spinning neutron star that has a strong magnetic field, there are a couple things that can happen. One is that, sure, it's radiating neutrinos. Sure, that causes that boiling and roiling, and maybe sometimes it causes a weak explosion, maybe sometimes a big explosion. But if you're rotating fast enough and you have a big magnetic field coming off of you, then what happens? So all you have to do is imagine me with a stick that's, let's say 50 kilometers long, and a little bead on the end of the stick, okay? And then all you have to do is imagine me rotating 1,000 times per second.
Give it a try.
And what would happen if I put a little metal bead right here, right down here, a little metal ring, and then this thing was 50 kilometers long, and I could rotate 1,000 times per second? It would come off at incredibly high velocity, okay? Incredibly high, in fact, very near the speed of light. And that is the type of models that we're making right now, are trying to explore that kind of collapse where you have a baby neutron star and you have magnetic fields sticking out of it, and the matter is being accelerated outwards like beads on a wire. And we've done a bunch of different calculations of that. I could show you some movies. But I think I'm going to conclude and just say, what are the questions? How do massive stars explode and why? I try to give you, first, if you lined up 100 astrophysicists and you said, how do massive stars explode? Most of them would say neutrinos, neutrinos. And then some of them would be like, but the explosions they get are not really very good. But we're figuring it out, okay? That's the answer to why they explode. Which stars explode and which don't? They would be like, we see some low mass stars explode. We've seen some 12, 13, 14, 15 solar mass stars explode. We saw 1987 explode. But there are some stars we're not seeing 20 solar mass stars, 25 solar mass stars explode, and we don't know why. What are the stakes? The stakes I mentioned are oxygen in your air and water and sugar. You know, my mom calls me, we talk on the phone. She says, why are you doing this? Why are you spending all this time on supernova explosions? That's my basic answer. My basic answer is that nothing would exist without oxygen. I also mentioned gold here because I could tell you about that. So the answers, I think there are a lot to be solved. I think the models both catastrophically fail and spectacularly succeed, but so does nature. The question is, are the right models failing and the right models succeeding and vice versa? And I think we don't know. What we're trying to do, what Kachanik and Stanek and me and other people at Ohio State and elsewhere are trying to do is we're trying to get the best census of supernovae, the best census of the stars that explode as supernovae, the best census of the black holes that we know exist, the best census of the neutron stars that we know exist, and we're trying to fit those together to figure out whether or not when you look at a star like Mintaka or Beetle Juice or Eta Carina, what's its outcome and how sure are we of that? So that's it. I'll stop there. Thanks very much. Yes, please go ahead.
So I'm the resident beginner here.
Yep.
I'm fascinated by the oxygen. I'm trying to imagine, you know, do astrobiologists get really excited with you guys because the regions around stars that go supernova, is oxygen a local phenomenon? How does oxygen sort of transmit
Yeah.
solar systems?
Yeah, so the way you should think about it is, you know, some little supernova goes off here. And on the scale of this, thing, that supernova blast wave, as soon as it goes off, not very long after it goes off, a few thousand years after it goes off, maybe 10,000 years, it really slows down. And what happens is it mixes with the matter in the interstellar medium. And the matter in the interstellar medium, the vast majority of all the gas everywhere in the universe is hydrogen. The next most common thing is helium. Everything else is less common than that and was mostly made by the stars. So when you look at this, this is basically all hydrogen and dust and helium, and that thing enriches that local area. But the thing is, that patch has already been enriched by the guts of millions and millions of supernovae over time. And so then what happens is you get just gas blobs, like these gas blobs. So this region in the Carina Nebula, is basically gas enriched by all of those supernovae, but over a billion years or even a few million years, and the gas comes together and then it starts collapsing and fragmenting. And when it starts collapsing and fragmenting, it's collapsing from gas that kind of has imprinted on it all of those episodes that contributed to it over the last millions or billions of years. Then those things collapse and form new stars, and those things collapse with protoplanetary disks, and then you've got solar system. So you should be thinking of it like
the Orion spur is not too far from us. Would something that happened in Beetle Juice reach anywhere close to our arm of the Milky Way?
So yeah, so Beetle Juice is only 600 light years away. That's about 200 parsecs. If it went supernova right now, in about 100,000 years, its supernova remnant would get about 1/100th the way, not 1/100th, no, about 1/50th of the way to us. So it would be, after 100,000 years, it would be like a big thing that you would see, big thing on the sky. And then what happens is that then, you know, the galaxy is just swirling and that gas gets mixed into other gas that's nearby. You know, Orion's very complicated. There's a bunch of stuff going on, some stuff in the near side, some stuff on the far side, star forming region here, which you all know very well. But there's also a bunch of gas all the way around it. So then you just imagine that thing just kind of get incorporated into the general motion of the galaxy. And those atoms would get mixed in with everything else over those long time scales, and then they would collapse again to form new stars. So the stars are, you know, essentially enriching future generations. That's the way to think about it. Yeah.
Has anyone like tried to calculate sort of how long after the formation of the universe that you know you have enough that enough enrichment of the elements for life as we know it to form.
Yeah, really interesting question. So once you start thinking about it, right, the universe began as basically pure hydrogen, pure helium. It's tiny trace amounts of deuterium, lithium, beryllium, and boron, but nothing else. So you really need carbon, nitrogen, oxygen. I mean, for life as we know it, you need phosphorus and DNA backbones and all kinds of stuff. It's a lot of complicated things I don't know hardly anything about. But people have tried to calculate that. So you start off, there's a first generation of stars. Those first generation of stars produce the first generation of elements. Then maybe you produce dense regions which can form complicated molecules. And then, you know, you collapse to some solar system that finally has enough for life. But do we know of a critical amount of oxygen or enrichment for? So there definitely has to be a minimum, because you have to be able to produce even some basic first prebiotic molecules. So those require a certain amount. Yeah, you were going to say?
I think their argument, I'll have to try to find the paper again. Their argument was, you know, it took maybe 6 to 8 billion years for these sufficient quantities.
But that would be in our galaxy, it's taken a while to get up to the amount of to basically build up so that you have stars that are forming that are so enriched like our sun. But the thing is that in other galaxies, like big elliptical galaxies that we observe, those galaxies became metal rich much earlier than we did. So that's why I'm not sure how long it would take. Maybe life is abundant in elliptical galaxies where there's there has been already lots of enrichment even very early in the universe. Yeah, at least as enriched as the Milky Way. Yeah. So big elliptical galaxies can be as enriched. They're sometimes more enriched in other elements, but they're very rich in we call everything above hydrogen, helium metals in astronomy. So we say they're very enriched in metals. That's what we say. That's our words. Other questions? Yes, sir. No. So what's going to happen in the sun is it's going to exhaust its hydrogen in the core, and it will be left with a helium core. It'll become a red giant, just kind of a normal red giant. Then it will burn that helium into carbon and oxygen. And then it will become a white dwarf. So what's going to happen is that the envelope will be ejected, and it'll be one of these planetary nebulae that you've seen, like the cat's eye or some of those other pretty planetary nebulae that leave behind a carbon oxygen white dwarf, which is about the size of the Earth. You know, similar size to the core. That's one of the ones here. This is a planetary nebula of the kind that the sun will produce. Planetary nebula of the kind the sun will produce, and then nothing happens. The white dwarf just cools off forever, as far as we know, and it just cools off, and that's it for eternity. We might have a very beautiful nebula around us. So, you know, planetary nebulae are quite. I still didn't hear you. What did you say? That's right. Yeah. That's important. That's important. So our star just evolves, becomes a carbon oxygen white dwarf, and nothing happens, and the CO white dwarf just cools forever. In binary systems, again, if you make a CO white dwarf, a carbon oxygen white dwarf, you can have a binary companion, and that binary companion can drop matter onto this guy, form an accretion disk, and then you can make what we call a thermonuclear supernova, type 1a, or white dwarf supernova. Those are very important because all of your iron is from those. But that's rare. But it happens once every couple centuries in our galaxy. And Tycho was walking home. Tycho, you know, the observer, was walking home, and he saw a new star in Cassiopeia, actually. And if we go look in that direction, now we see the guts of a CO white dwarf, a thermonuclear detonation of a CO white dwarf that probably happened in a binary, some kind of binary system. But our star will just cool off forever. And that'll be that, unfortunately. Yeah.
I got a question for you.
Go. No, go ahead.
I thought at the end of a main sequence star life that the white dwarf wasn't exactly dead because it keeps glowing.
Yeah, so I think the current status of that, I'm not the world's expert on that, but there was a dimming episode about 4 years ago. Beetle Juice got noticeably dimmer. What's amazing about Beetle Juice and other red supergiants, when you do computer simulations of them, they have huge convective cells. So if you think about the sun has tiny little convective cells all over its surface. Have you ever seen those beautiful H-alpha images where they really zoom in and you can see a lot of structure on the surface of the sun? In Betelgeuse, you should imagine, like, if this is it, the surface can be very deformed actually from a sphere, because there's big convective motion over here and there's another big convective motion over here and another one over here. So it has a very strange kind of shape, and it can have a lot of temperature variations because those big plumes that are coming up and down are gigantic compared to the star. So there are only like 10 of them. So it almost looks like, I don't know, almost looks like a I don't know, a 10-sided polygon that has hotter and cooler spots. And so the what I've heard is that that's probably what we were seeing. We were seeing a big downdraft pointed towards our line of sight, that it was cooler receding material.
Well, the question I had was,
I wish it did. People were very excited that maybe Betelgeuse was about to explode. And I just, I hope, but yeah.
Well, the question I had was, I thought at the end of the
so there was
star's
also
life,
a claim that it belched dust. That's right. So when this Betelgeuse is very cool, and if you just put out enough material and it cools off as it goes away, dust can absorb it. You were going to say something? Jumping ahead? Oh,
yes.
It's almost like a giant sunspot. Yeah.
Talk about gold in your talk. You probably cut that short. I'd like to go back to that for a second.
Sure.
In the last 10 years or so, it's entered into the lay press that heavier elements in the universe, and notably gold.
Yep.
The general idea for up until the turn of this century was that heavier elements were produced in supernova explosions and splattered out into space. Normal single stars blowing up and that kind of thing. But it turns out that that is not sufficient to produce the amount of those elements that we see.
That's correct.
And the alternative mechanism for producing gold in particular was neutron star collisions.
These ones,
And it seems to me, I mean, just thinking about it, that a neutron star merger would not be all that common. And the reason why is because your two stars are starting off pretty far from one another. And they lose energy by producing gravitational waves or whatever. And that, if they're really, really far, the amount of gravitational waves that they're producing is not a lot.
Well, they have to be close, that's right.
And so they have to be close to begin with. So I'm wondering what the dynamical process that brings them close together to begin with is. To the point where they're actually producing a lot of gravitational waves, and they're falling into one another because they're losing rotational energy. What's going on?
Okay, I'll tell you about that real quick. So what Brad said is right, that 20 years ago, 30 years ago, it was thought that all of the rest of the heavy elements, or most of the heavy elements above iron, were made in supernovae. About half of them. The other half are made in other type of star, but about half of them were made in supernovae. And the thing is, you don't make them via fusion. You don't fuse these elements. So if you pick an atom like gold or platinum or uranium, gold or platinum or uranium, it doesn't get made. It doesn't get made by fusion. What happens is it gets made by what we call neutron capture. So if you take here, let's again zoom in on an iron nucleus. Here's an iron nucleus, 26 protons, 30 neutrons. And you take a fire hose and you just blast it with neutrons. Every now and then a neutron will get stuck in the nucleus, will capture. What does that do? It makes a weird isotope of iron. It makes a neutron-rich isotope. Imagine you fling 10 neutrons onto this thing. It makes a crazy radioactive isotope of iron. But what happens is that some of those neutrons, through a process called beta decay, they turn into a proton. It's actually related to the neutrino interaction rate I showed you before. So you have a neutron-rich isotope, and 10 of those neutrons beta decay to protons. And now you've gone up the periodic table from 26 to 36. I don't know which one that is, but you've made a new element from beta decay after you've captured neutrons. That's how heavy elements are made. So my PhD thesis in one of my papers, my second paper I ever wrote, was on trying to calculate whether or not you can produce those heavy elements in supernova explosions. 2001, I wrote this paper right at the turn of the millennium. And we found, and there were about 3 papers all at that time who found that you can't do it. The conditions are not right to produce those heavy elements, and supernovae cannot be doing it, not normal supernova explosions. So that really was settled at around 2000 to 2003. 2000 to 2003, the community was like, this is not good. It seems like supernovae can't do it. At the same time, there were a bunch of people doing these kind of calculations of neutron star mergers. And what they find when these neutron stars merge, they fling out these ribbons of material. You see that? Those ribbons are moving out at almost the speed of light, and they're almost completely neutrons. And as they come flying out, what happens is they cool off. Some of the neutrons convert to protons, and it's so dense and it's expanding so fast that this literally produces outflowing ribbons of gold, europium, silver, uranium. And so you form a black hole in the center, but at the same time, all this material is flying out. And an event like that was actually seen in 2017. A nearby elliptical galaxy had an event shown here that was the merger of 2 neutron stars, because we detected it with LIGO, and it flung out all of these heavy elements, which we could confirm. Now the 2 questions were, one, these events are rare. I mean, supernovae are already rare. Now we're talking about 2 supernovae that happen to make 2 neutron stars, and it has to be 2 neutron stars that are close enough that they'll merge together. That event is rarer than a normal supernova, but when they merge, they eject a lot of material. So there's almost, they eject like half a solar mass, or not a half a solar mass, about 0.2 solar masses of material can go flying out here. And so you imagine just, 0.2 times the mass of the sun in gold, europium, uranium, platinum, and so on, flying out into space at 1/10 the speed of light. Now the question is how do you get stars close enough? Because if you have 2 neutron stars that are separated from like the distance of the sun to, say, Jupiter's orbit, they never merge in the age of the universe. You have to have 2 neutron stars that are born very close. But stars are already big. So, if you have 2 stars that are, even if they're touching, even if you have a binary system where the 2 stars are nearly touching, which is possible, 2 massive stars are nearly touching, they're going to evolve and they exchange material. And then the process that brings them super close together is a thing called common envelope evolution. So what it is you have a star here. This star is swelling up, and envelops this star. So it's actually in one massive star evolving and enveloping the other one. And when that happens, this star meets a headwind of all this material, and the cores actually get very close together, and the rest of it is ejected. And so it's through this process of very close binary evolution called common envelope evolution, where one star evolves and envelops the other, that you can get 2 cores that get really close to each other, such that when they finally collapse and form neutron stars, they're close enough to merge in. Yeah, it's like drag, and it's the process of throwing out the envelope takes away energy and angular momentum from the orbit. So that's the actual physical process that happens. Yeah, no, it's an interesting variation on the whole picture. So I would say right now, if you lined up 100 astrophysicists, they would say probably most of those heavy elements come from neutron star mergers, but there are still some problems with that, some things we definitely don't understand, and some strange supernovae Maybe rare supernovae where the neutron star is rapidly rotating and magnetic. Like that powers, as I was talking about, those rapidly rotating, highly magnetic neutron stars, when they're born, they actually might make heavy elements too. And so right now there's a discussion in the literature is it all neutron star mergers, or is it neutron star mergers and also these stars that collapse and form rapidly rotating, highly magnetic neutron stars? Or maybe it's stars that collapse to form black holes with a big accretion disk, not like the one that we found. We don't know. Slow neutron capture is another way to make heavy elements, and slow neutron capture happens in normal stars. In normal stars can make some heavy elements. About half of the elements above iron are made by this slow neutron capture process. Both of them are neutron capture. One's just fast. The one I described to you is fast. The other one is slow, and they make a different distribution of elements. But oh yeah, if you want to make gold, I mean, many of you probably have gold on your hands right now. Those gold atoms, I mean, we think those gold atoms came from neutron star merger in the universe.
Neutron star pairs are a little more common. There's at least a dozen.
There are neutron star binaries that are known for sure, and there are more than a dozen known, and several of them will merge in the next just couple 100 million years. That's right, for sure. It's just that you still, not only do you need to have the mergers happen, they need to eject enough stuff, because you sort of know how much gold is in the universe. You go and look at stars and you can measure how much gold, platinum, uranium they have. You know you need to make that much. That means there have to be this many neutron star mergers ejecting this much mass. And so that's the question, is do we see those? Right now we've only seen one event. Anyway, I can keep going, but thank you.